We'll now return to the questions that we asked in the very beginning of this lesson, starting from genomes. How can we transform them into Synteny blocks? And the first thing I want you to learn is the notion of genomic dot plot. Let's arrange genome along x coordinate and along y coordinate. And let's represent every chimer that is shared at position x and y in the genome as a dot at position with coordinates x and y. In this case, I show you genomic dot plot for chimer size equals 3, and it only consists of the diagonal in the genomic dot plot. Of course, diagonal is always present in the genomic dot plot because chimers at the coordinate x and x are always the same. But here's the genomic dot plot for k equal 2. And you can see that in this case the number of dots increased as compared to k equals 3. For example, these 4 dots correspond to repeated occurrences of the 2-mer CT in the genome. So far, we talked about genome consisting of one strand, but in reality, of course, genome consists of 2 strands, and therefore we should take care of both identical and reverse complementary chimers while representing genomic dot plots, as shown here. In this case, red points correspond to identical chimers, and blue points correspond to reverse complementary chimers. Now, this is how genomic dot plot looks like when we compare a genome against itself. But can we also construct genomic dot plots when comparing 2 different genomes? And here's an example of comparing one genome with another one that is obtained from the first one by a reversal. And in this case, you can see that a reversal corresponds to -45-degree diagonal formed by blue points in this genomic dot plot. Now, from looking at the small string, let's now construct genomic dot plot for entire E. coli and Salmonella genomes, and human eye immediately see Synteny blocks in this genomic dot plot. They simply correspond to various diagonals. And we only pay attention to sufficiently long diagonal because small diagonal or small points, clusters of points, may represent noise in this case. So we see 5 Synteny blocks, 5 diagonal corresponding to a block marked as A, B, C, and D, and E. And if we project these blocks on x-axis, we will get an arrangement of Synteny blocks in E. coli. And if we project them on y-axis, then we'll get an arrangement of Synteny blocks in Salmonella. And now we are ready to analyze the 2-break distance between these 2 genomes. Therefore, construction of Synteny blocks essentially amount to constructing diagonals in the genomic dot plot. And here's finding Synteny blocks problem. Input is a set of points in genomic dot plots in 2D, and the output is a set of diagonals in dot plot representing Synteny blocks. Does it make sense? Of course it doesn't make sense, because I have not defined what diagonals are. Look at this genomic dot plot, and you can see that diagonals are not perfect because there are many insertions, deletions, mismatches, and many other artifacts. And therefore, human eye has ability to somehow process this genomic dot plot into 5 diagonals, but we really do not know what our brain is doing while making this transformation. Can we come up with an algorithm for constructing this diagonal? Let's try. Let's look at the genomic dot plot between 2 different genomes that we constructed before, and let's represent every dot in the dot plot as a node in the graph. And we will form edges in this graph by simply connecting closely located points. for example, points that are located at distance less than max distance, where max distance is a parameter. What will happen? We will connect certain points by edges, and you can see from here that diagonals actually correspond to connected components in this graph. Moreover, we probably should ignore a very small connected components, for example, a component located in the upper right corner and lower left corner, but the three remaining components should be accepted as Synteny blocks in our genome. And therefore, I offer you the following algorithm for solving the problem. Let's form a graph whose node set is the set of points in dot plot, and connect two nodes by an edge if the corresponding nodes are located at close difference from another. The connected components in the resulting graph define Synteny block, and afterwards delete small Synteny blocks. Of course, this is not the only algorithm that tries to model what the human eye is doing while clustering points in 2D, and our brain is very good at clustering. I can give you another algorithm, for example, this one that I call amalgamate. And it's actually different, but it looks like it's doing almost the same thing. First step, define each point in dot plot as a separate block and iteratively amalgamate the resulting block. How do we amalgamate the blocks? We amalgamate two blocks and combine them into a single block if they contain 2 points that are separated by a small distance in another genome. And as before, delete small Synteny blocks. So we have a problem, and we have two algorithms for solving it. Which algorithm would you use? Instead of answering this question, you should ask me what problem I actually want you to solve. Because I have never defined an algorithmic problem that I want you to solve. You should have refused coming up with an algorithm before actually seeing the problem I want to address. Unfortunately, in bioinformatics, it's not as simple. I have been working on the problem of Synteny block generations for 10 years now, and I failed to formulate this problem as a rigorous algorithmic problem. And that's why we are at mercy of our intuition. And some people may like Synteny algorithm better, other people may like amalgamate algorithm better. How would we choose? The choice should be done based on the practical results. And if you implement this algorithm and run them, then you see that Synteny algorithm gives reasonable and biologically adequate result. But amalgamate algorithm, also it looks reasonable, it looks like it models what human eye may be doing, gives completely wrong results. After developing the algorithm for constructing Synteny blocks, we are now ready to find out what are the Synteny blocks between human and mouse X chromosome. And here is the genomic dot plot for the X chromosome, consisting of 25,000 dots. We form a Synteny graph on these 25,000 nodes, and in this slide you can see the resulting connected components. We further process these connected components and represent them as perfect plus 45 degrees or minus 45 degree diagonals in 2D. Where are the 11 Synteny blocks between human and mouse that we have been considering in this lecture? Well, if you project these 11 blocks in 2D to x-axis, you will get the arrangement of human Synteny blocks. And if you project it to y-axis, then you will get the arrangement of mouse Synteny blocks. Moreover, since we are not particularly interested in scale of this block, and even if some blocks appear small, there are maybe hundreds of genes in each of the blocks. It's just an issue of scale. So let's represent each block by the diagonal of the same size. And once again, if we project these blocks in 2D to the x-axis, we will get arrangement of Synteny blocks in Phillip. And if we project it to y-axis, we will get the arrangement of Synteny blocks in mouse. And now, after we constructed Synteny blocks for 2 genomes, How about constructing Synteny blocks for 3 genomes? You can think about generalizing our Synteny block construction approach to more than 2 genomes. But what about constructing Synteny blocks for 100 genomes that are being sequenced now? This actually turns out to be a very difficult problem, and nobody in the world today is able to construct Synteny blocks for 100 genomes. Maybe after this course, you will suggest a reasonable approach for this. But interesting thing is that if we learn how to construct Synteny blocks for many genomes, we will be able to come up with a very accurate picture of chromosomal organization in our distant ancestor. So there is a lot of work ahead in developing genome rearrangement and Synteny block construction algorithm, but this is already beyond the scope of this course.